Over the course of my studies in theoretical physics, I've traveled across the continent and around the world sampling new ideas and tasting different answers to the questions of how and of why. And still, I find there remains a deep hunger which lives within me, a burning desire to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicist Podcast, and I'm Ben Tippett. And now, allez, physique! Okay, gravitational collapse 101. Let's consider what happens when we let a cloud of gas, say hydrogen, out in space, collapse under its own weight. First, the cloud's going to collapse to a ball whose radius, whose general size is maintained by the thermal pressure of the gas. Because as the gas collapses, it's going to gain gravitational potential energy that's going to turn into thermal energy, drive a pressure that keeps the ball aloft. But gradually, the ball will cool and radiate photons out to space, and this radius is going to decrease, and the pressure inside the ball will increase, until maybe it can trigger nuclear fusion. If the ball isn't heavy enough, it won't be able to trigger this nuclear fusion, and we'll end up with something called a brown dwarf. But if there's enough mass in our ball of gas, nuclear fusion will start in the center, and we'll get a star. Now, in a star, the photons liberated by the fusion taking place inside the core will blow out like a steady wind from the center, puffing out the radius of the ball of gas, and that will hold the radius of the star aloft. But eventually, the star's going to run out of fuel, and it'll start to collapse under its own weight again. Then what? Well, novas, supernovas, fairly complicated thing, but what you end up with at the end of the day is that if your ball of mass is smallish, it won't exceed something called the Chandrasekhar limit, and it will collapse down into a white dwarf. Now, a white dwarf is a system where the electron degeneracy pressure, a quantum mechanical pressure, will keep it from collapsing down any farther, and you'll end up with this lump. But if the ball is a little bit heavier than that, maybe around 3 solar masses or less, the pressure from the gravity is going to be so strong that the electrons are going to get squished inside of their protons and all the atoms, and you'll end up with essentially a nucleus, a big pile of neutrons. And only neutron degeneracy pressure, another type of quantum mechanical pressure, will keep it from collapsing down any further, and we call this object a neutron star. Now, it's not clear whether there are any more steps down the ladder of gravitational collapse, but we do know that below the bottom rung lies the most exotic of the celestial objects, a black hole. Now, a black hole is what you get if you let matter get so dense that it punches a hole in spacetime itself. In layman's terms, a black hole is an object made of nothing but gravity. And unlike any of the previously mentioned astronomical objects, which have a surface that you can punch and throw rocks at, black holes are defined by their event horizons, causal out-of-bounds lines, which can be thought of as boundaries for the black hole. Now, the acceleration due to gravity is so strong at an event horizon that any outgoing photon, which moves at the speed of light, will barely able to sit still on that boundary, hence the name black hole. So the question we're going to ask today is, can we actually see these objects? How can we see something that doesn't actually emit any light? Today, my guest is Kelly Weinersmith. Say hi, Kelly.
Hello!
She's a PhD student from the University of California, Davis, where she studies parasites and behavioral ecology, right?
True.
And she's the host of The Weekly Weinersmith, a new podcast starring her and her husband, Zach Weinersmith, who is famous for webcomics.
Saturday morning breakfast cereal.
That's right. And Kelly has also submitted a research proposal to the Sci-Fun Challenge. Do you want to tell us anything about your proposal?
Sure. So the proposal is to fund my research looking at brain-infecting parasites and their effects on behavior, which is a totally cool topic to begin with. But actually, the awesome thing about the proposal is that it is the only proposal to already be funded. And so you should really check out scifun.rockethub.com and look at the other projects that aren't funded yet. And there are 48 of them, and they're all equally awesome.
That's magnificent. All right, Kelly. So, you and I are friends from science, sort of, and today I've assembled two of my very best titanium physicists. Arise, Dr. David Sang! Now, Dr. Dave was an undergraduate at UBC with me, but he did his PhD and master's at Cornell. He's currently at Caltech working as a postdoc astrophysicist. Now, my other titanium physicist, arise, Dr. Jocelyn Reed!
Roar!
Good. Dr. Jocelyn did her undergraduate at UBC, her PhD at the University of Wisconsin-Milwaukee, and she's currently at the University of Mississippi working on neutron stars. All right, guys, let's start telling Kelly about these black holes and whether or not we can detect them.
Okay, so one of the defining things about a black hole is that there's no surface. If you are falling into a black hole, you would just fall in without ever hitting anything, and you would sail right through the horizon, down into the center, be cut off from the rest of the universe, and, well, who knows what happens then, but there's no running into the surface of a black hole.
Do you fall forever?
Well, I mean...
No, you don't.
You would hit the singularity in the middle and get
crushed. Right.
And plus other bad stuff's probably happening.
You get sort of stretched out into spaghetti.
Well,
so instead of getting crushed, you get stretched?
You get stretched by tidal forces. But it depends. If the black hole is very, very large, you won't.
For a while. Eventually you get crushed.
Yeah.
Right.
So I had kind of thought that black holes, you get sucked in, and then there was something about black holes are an area where there's a lot of gravity, so I had always imagined you would get squished instead of stretched. Can you explain why you get stretched?
So Newton's law of gravitation tells us that the force of gravity falls off with distance as the distance squared. So something that's closer to another object feels the force of gravity stronger, right?
Yes.
So in what are called tidal forces, the difference between your feet and your head as you're falling into the black hole, there's extra force on your feet compared to what's on your head. So you'll feel this sort of pulling you apart.
Ah, okay, I got it.
So it's a stretching.
Here, I've got a crazier one. All right, so first off, the tidal forces from the moon are what cause the tides. And so a gravitational field from the moon, it's like a pair of fingers squishing the Earth so that there's a bubble of ocean above, behind the Earth and a bubble of the ocean facing the moon. But it's kind of like this. Imagine that you had a colander. So it's a nice round surface, and then you have like an orange, which is another round surface. Now the curvature of these two don't match. And so if you push the orange into the side of the colander, the face of the orange will get all deformed and smushed out as it has to try to conform to the face of the broader surface. And that's essentially what happens in these tidal forces, is that the curvature of gravity becomes so different in different directions over an elongated body that it ends up effectively pulling you lengthwise and squishing you widthwise.
I see. I think I followed David's thing better. I'm sorry. I guess this isn't a contest, huh?
The appetizer course goes to Dr. Dave.
Oh.
So the thing about black holes is that it turns out that you can observe black holes astronomically.
Right. As stuff falls into a black hole, it'll heat up just because it's gaining kinetic energy because it's dropping through a gravitational potential. So as this stuff heats up, it starts emitting light just because it gets hotter and hotter. Just like if you heat something up on a fire to really hot, it starts glowing. So we can learn a lot about black holes, even though we don't get light from them directly, by looking at stuff that falls in.
Well, hold on, Dave. So when we say stuff falling in, black holes are usually surrounded. Well, the black holes that we can see usually have some other gas around them that's in the process of falling into it. So it's usually kind of swirling around the middle, trying to enter the black hole around the equator.
That's right. It's called an accretion disk.
Right, an accretion disk. And when stuff tries to fall into the black hole, it ends up running into that accretion disk. And it's like if you dropped a bowling ball off a bridge and it slams into the water, and then the water absorbs all of the gravitational energy, right? So So what we see is the accretion disk heating up.
That's right. So the accretion disk, as it's swirling around, it rubs up against itself. And that friction causes it to heat up. And that's the energy that we're seeing. And this can get really hot, out to X-ray temperatures. So we can actually observe these accretion disks in the X-rays as they're falling into black holes.
So we take an X-ray telescope and we look out and we see all these bright spots. And those bright spots are black holes.
That's right. Or they could also be neutron stars.
Yeah.
Neutron stars also have something similar where, so these accretion disks usually come from the binary companions of these objects. So you can have a black hole or a neutron star with a large main sequence star or a giant star that it's in a binary orbit with. And as this binary gets closer and closer, the black hole or neutron star starts stripping away material from its companion. And that material sort of sluices down and forms this accretion disk around the compact object.
Right. And so we see these binaries, and one of them is a star, so we can look at it in visible light, and we can say there's a star. And then when we look at it closer, we see that it's orbiting something, right? So we see the star getting towards us and going farther away from us back and forth periodically. And then we see that the object it's orbiting isn't bright.
That's right. So, and based on how that star is moving, we can look at the Doppler motion of its spectral lines, for instance. We can sometimes infer what size the companion object must be. So we can see from the way a certain star is moving that it must have a very massive object that's moving it around.
Right.
And that's often how we can infer the size of black holes.
So I know what Doppler motion of its spectral lines means, but that sounds like something most people wouldn't know.
So if you have a spectral line, it's just a transition line from a particular atom that's been excited. And
so it's just light of a particular frequency, that it's always at the same frequency because the same process happens.
That's right. And so as the star sort of moves around in an orbit, that gets Doppler shifted, bluer and redder as it's going around. So just like as a siren moves past you, it gets higher pitched and then lower pitched. It gets higher pitched as it's coming towards you and lower pitched as it's going away. You get something appearing bluer when it's moving towards you and redder as it's going away. And that's the Doppler shifting of a spectral line.
Yeah. I want you to imagine a merry-go-round where you've taken kids and you put them on the horses on the merry-go-round, and then you've turned up the speed of the merry-go-round really fast, so they're all screaming. And if you do it fast enough, all the kids will scream at the same pitch, but on the merry-go-round as they go around in the circle. On the side that's moving towards you, their screams will be Doppler shifted, higher frequency, and the ones moving away from you on the other side, their screams will be Doppler shifted to a lower frequency. So one side will sound like, ah, and the other side will sound like, ah, even though they're really going, ah. You get it?
I do. You shouldn't be a parent.
Now imagine you have one of these children, and they're being spun around by a very fat man. Based on the speed of that spinning, we can tell how big that fat man is.
All right.
Well, actually, based on the spinning, you can just tell how big the combination of the kid and the fat man is.
That's true.
Right.
That's true.
So how do you tell the difference between the fat man being a black hole and the fat man being what did you say, a neutron star?
What an excellent lead-in question.
Holy crap.
Oh, I'm good.
So, the difference between, if you remember, the difference between a neutron star and a black hole, or one of the differences, is that a neutron star has a surface. A neutron star or a white dwarf, they have surfaces. So, as this material is falling in, if it falls into a black hole, it passes through the event horizon and is lost to our universe. It can't get back out again. But as when it goes onto the surface of a neutron star, it can sort of build up there. And this material can sort of build up and up and up until there's enough material that gets hot enough to start fusing, and you get what's called an X-ray flash. And that's one of the ways we can actually tell the difference between neutron stars and black holes is systems where there's a surface for this material to build up on are thought to be neutron stars, whereas systems where we never see these flashes are thought to be black holes.
So if the kid throws up, you'll see it on the fat man.
Right, if the fat man is a neutron star. But
right,
if
otherwise it disappears.
Pulls up all the puke, then he's going to be a black hole.
I got it.
And we have some idea before we look at the bursts, which ones are neutron stars and which ones are black holes. Because neutron stars can only be so fat, right? Because they're like matter's last stand against gravity, right? So that's the nuclei or the neutrons are going as fast as they can, trying to keep the star from collapsing. And at some point, if you add enough mass to this, it'll collapse to a black hole. There's a limit as to how big this can be before it just can't support any more weight. So if you know from the binary thing that this, whatever the compact object is more than about 3 times the mass of the sun, then you think it's going to be a black hole. And if it's less than that, and then you think it's going to be a neutron star. So you can look at these things and you can say, oh, look, hey, all the ones that are bigger than the neutron stars aren't showing these flashes.
Okay.
So the black hole picture totally makes sense.
So how do we know that there isn't something denser than a neutron star that isn't a black hole?
Well, we don't. There actually could be things that are denser than sort of a typical neutron star, but still not a black hole. So the neutron stars, the idea is that degenerate neutrons. So, okay, when we say degeneracy pressure, this is like a quantum uncertainty thing. The faster something is moving, or the more precisely you know the speed something's moving, the less precisely you know where it is, and vice versa. So this is like an uncertainty principle. And so if you're trying to squish a lot of things into a small area, you are localizing them, therefore they have to be moving with uncertain speed, so they're moving fast, and this is a pressure that keeps it from collapsing. So it could be these neutrons in a neutron star providing this pressure, but you could also actually imagine a further collapse where instead of a bunch of neutrons going around, you actually have quarks. So each neutron and proton is made up of 3 quarks, and you could actually have this fluid of quarks that's supporting a quark star. So you can have these various things. And so this is one of the questions actually is there's some possibility that you could have these strange stars that would be, well, it's very hard to make them denser, or you can't easily make them support more than 3 solar masses. But you could have these other kind of... Huh?
What's a solar mass?
The mass of our sun.
Oh, okay, thanks.
So yeah, whenever you're talking about gravity, most of the time you can measure things in terms of solar masses better than in terms of kilograms.
A solar mass is about 2 times 10 to the 30 kilograms.
Whoa. All right, got it. And we use our sun as the standard.
Yeah.
Okay.
So I think that one way we can talk about this is in terms of surfaces, right? Dave was talking about it earlier. Any ball of matter is going to have some surface, some kind of outer edge. And so even if it's one of these weird, what's it called, a strange star?
Quark star.
Oh, okay. So if it's made of strange quarks, then it's called a strange quark star?
Yes.
Unlike the, uppity quark stars. So I think one interesting way to look at gravity, black holes specifically, is in terms of this analog system where you imagine the black hole, the gravity in the black hole, as a waterfall. Okay, so there are fish in a stream. Let's say it's Niagara Falls. Up the Niagara River, there are fish in the stream, and they can talk to each other, let's suppose. And they talk to each other with sound waves. Okay? Mm-hmm. Now, there's a point at which the water moving through the air moves faster than the speed of sound in water, if the waterfall is high enough. All right? So this is an acoustic horizon. And what it means is any fish farther down the waterfall than that level, they won't be able to talk with the surface, because when they try to squeak it at each other, the sound waves can't move up the waterfall because the water is moving down vertically faster than the sound waves can move up, okay? Mm-hmm. So this acoustic horizon is the analog to our event horizon in gravity. The role a boundary of a star plays in the system is it's like a grate. So it's like, Niagara River Council people said, okay, we can't have people going over this waterfall, so we're going to put a grate across the river, and that's going to keep anything from falling past a certain level. Mm-hmm. So they put an iron grate across it, and then stuff can build up on the grate. And so any object in our gravitational system, any compact object that's bigger than a black hole, will act like one of these grates. And so matter that falls in on the object will just pile up on the surface of it. And Dave was telling you earlier about how fusion can happen in gas once it hits the surface. So the idea is that, what would you say, hydrogen gas is kind of like an egg, and that if you hit it hard enough, fast enough, it splatters and you can make something new with it?
That's not what I would say.
maybe that's what you should say, Jocelyn. Okay, so anyway, flashes of fusion start to take place as streams of matter go down and hit this surface, this grate. And so this is a characteristic feature that we'd see in any system where you have a compact body that is larger than a black hole, right?
That's actually the thing about strange quark matter is that, so pretty much any matter, yes. But there's this idea that strange quark matter would be more stable than regular matter, like sort of an Ice 9 scenario, if you've ever read the Vonnegut book, where there's this form of water that's solid, that as soon as one crystal touches it, the water can collapse down to this more stable state and the Earth freezes. So there could be this strange matter which does the same thing. And so if there was this particular kind of sort of crazy model, which is hard to be compatible with some other things, but if stuff accreted onto that, it could just immediately get converted to strange quark matter with giving the thermonuclear bursts.
That's right. So it's like the blob.
Yeah.
I've lost track of the question we're answering.
We're trying to see whether something is a black hole or not. And the thing is that you can think of some sort of crazy scenarios that are technically not a black hole because there's matter there, there's a surface that's not in a horizon, but still hard to see with other ways. So we started up looking at these X-ray things bursting and saying, hey, look, the neutron stars burst, the things we think are black holes don't burst. That's totally compatible with this horizon idea.
I think the kicker here, though, is that now that we've got a theoretical explanation for why the only compact body that won't have these fusion bursts will be black holes, is that you can then go out and look into the universe and try to see black holes. When we do observations, astronomical observations, you can look for these binary rotating systems where one object is a big star and the other is a very heavy compact body that isn't emitting light. And then so some of them have these fusion flares and others of them don't. So the idea is that now we have a way to look at these, and there's a criterion that you can use to tell whether or not you're looking at a black hole.
So there's more than just black holes that are around this size. There are also some theories which predict smaller black holes from primordial formation that sort of zip around, and they don't really get into binaries with stars, so they can't accrete matter, so we don't see them.
They're moving?
They could be moving around. There's also what are called supermassive black holes. These are sort of the most massive objects in the universe, and they're thought to be at the center of galaxies. For instance, we have a black hole that's 4 million times the mass of the sun, located at the center of our galaxy, the Milky Way.
Wow.
It's in the Sagittarius constellation, right? So
it's
the spot is called Sagittarius A star.
Right. So the question is why we know that that's a black hole and not just some really big star or clump of other stuff.
So there's a bunch of different ways we can actually probe this. One way is just looking at how stars behave close to this object. So some people have basically been tracking for decades the
since 95.
Is that 2 decades? No, not quite decades.
15 years.
1.5 decades. The motion of certain stars that are very close to this galactic center, and you can watch these stars in a sped up animation. And as they sort of approach this one point, they suddenly whip around as if there was an extremely fat man there, grabbing their arms and throwing them around. And these stars just suddenly turn around in the spot and start moving the other way.
There's got to be something really big there, and that's how we know how massive it is.
That's right. That's how we.
Why do they whip around and not get sucked in?
They don't get close enough to get sucked in.
Okay.
So they're still quite a ways away from the black hole, quite a ways away from the event horizon, and they're also quite a ways away from what's called the tidal disruption radius, when they sort of get broken apart where they get stretched apart, just like you would get stretched.
Okay.
So there's sort of like comets that are orbiting the sun and just sort of come in on this crazy orbit, come close to the sun, and then whip around, and then we don't see them again for decades.
Got it.
So these are on a similar kind of orbits.
Okay.
I'm not sure if there are any other real examples that you can give where people are literally taking videos of stars flipping around each other, but this is I'll link to it on the website, but it's a very dramatic scene because it, honest to God, looks like a video of stars. Usually stars don't move fast enough relative to one another that you can see them passing each other, but these stars are honestly flipping around this central object, and you can't see the central object, so there's like a little X on it, and everything else is flying around it the way like paper would if you had a whirlpool in a drain and you threw some paper in your sink, and you'd see these papers just like whipping around this whirlpool, and you'd say, well, what's that? And the answer is, well, it's a black hole that we can't see. A very, 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 very heavy black hole.
So actually, also very recently, just this year, astronomers have been using what's called very long baseline interferometry, where they interfere millimeter wave, sort of near infrared radiation, and they're measurements from the galactic center, and they're almost able to resolve down to the event horizon. They're able actually to see hot spots from the matter falling into the black hole. And it's a very, very difficult measurement, and it will only get better as time goes on. But right now, they can start constraining things about the black hole, like how fast is this black hole spinning, how much stuff is falling into it, and things like that. So it's actually a very, very exciting time to be studying these things.
Awesome.
One thing that you see specifically around black holes, actually, the first test from general relativity, this isn't a phenomena specific to black holes, the very first test in 1919, when Arthur Eddington goes out into the wilderness because there's a full eclipse of the sun, and he wants to measure the distance to the stars. And what he shows is that starlight that should be traveling past us ends up having its trajectory warped by the gravitational field of the sun, and then ends up hitting Earth. So what you see is that these massive bodies end up bending light. And if it's a really, really, really compact object, like a black hole, you see it almost looks like a lens, the way it warps the light around it. And so Dave was mentioning some people who had done large-scale interferometry of the supermassive black hole at the center of the galaxy. In their images, you can actually see the light warping around this sphere. It's quite amazing.
Yeah, it sounds awesome.
Oh yeah, it's awesome.
That's right. Their resolution isn't quite good enough to be able to resolve the event horizon itself, but it's actually getting close. It's only on the order of a few times the event horizon now.
So what would knowing exactly where the event horizon is tell us? Why is that useful information?
It would be the first time we're able to directly image a black hole.
Oh yeah, that would be pretty cool.
I mean, what you see if you kind of look at a black hole against stuff behind it is this empty disk, and then around a ring, sort of around the horizon, you see all the stuff that would be behind the disk. The light from it has gotten bent around, so you see it in tiny compressed, squished things around the ring. And then in the center, it's just black.
Sort of like looking through the base of a wine glass.
Actually, if you have a Mac, I think one of the effects you can do in the photo booth will make a like black hole.
Cool.
Actually, using this gravitational lensing effect, but instead of using just one object, people use an entire galaxy. Recently, astronomers have been able to use this gravitational lensing to zoom in on what's called a quasar, which is a distant object thought to be very bright hot gas falling into a supermassive black hole at the center of another galaxy. And they can actually get an image of this disk of gas that's being sucked down into a supermassive black hole. You can't see the black hole itself, but you can actually make up the disk at this galaxy that's billions and billions of kilometers away.
Awesome.
It's been magnified by the mass. We use the distortion of masses of all the light coming from behind them to weigh how much matter is in different structures. This is one of the things that tells us that there's something called, well, I guess this is kind of getting ahead of the top or off topic, but stuff like dark matter, if you have heard of that at some point.
I have. We interviewed Sean Carroll about it very recently.
Okay, so you probably heard a bit about the bullet cluster, but it's basically you look at something that passes behind, or you look at stars that are behind something, and how much the light from those stars gets distorted tells you how much mass is in the stuff moving in front of them.
Got it. Awesome.
These are all these really super relativistic behaviors of curved space that we actually now see in very common astrophysical things.
Cool.
So, Kelly, do you now believe the black holes exist?
Yes.
Do you believe that they're out there and waiting to eat us?
Sure, and I believe we can measure them now in some ways.
Cool.
That's awesome. Okay, I consider that a victory. I can't think of any other reasons why we need to tell you anything more about black holes, Kelly, except for what happens when you fall in one. Do you want to know what happens if you fall in a black hole?
Absolutely.
All right.
I know you get stretched out.
So the question is, what happens if I see Jocelyn fall in a black hole?
Okay, I'll illustrate.
Right.
Oh.
If I threw Jocelyn over a waterfall, the sound that she made as she was screaming over the waterfall would be Doppler shifted as she accelerated down towards the bottom. Just in exactly the same way, the thermal light emitted from her body as she fell into the black hole would also be redshifted.
Or if I have a flashlight.
Right, if she had a flashlight, it would also be redshifted, as we mentioned before in the Doppler shifting example. As she fell in towards this event horizon, I would see her moving slower and slower and getting redder and darker as the photons that come off her clothing and travel towards my eyes got more and more energy sucked away from them as they had to climb up this gravitational well to arrive at me. And then so I'd see her fade away over the course of millennia. And in fact, it would take longer than the total amount of time in the universe for her to cross over the event horizon from our perspective. Whereas in her perspective, it would only take a second. And then she'd be stretched like spaghetti and crushed, but we'd all be dead.
I'd be like, why are you guys going so fast? No need to panic.
From her perspective, the universe would start going faster and faster, and then she would be crushed fairly quickly. So anyway, food for thought.
Unless it's a really, 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 really big black hole. So the bigger it is compared to me, the less I feel stretching from different parts of my body.
Yes.
It's like all a question of relative size between me and the black hole. So if it's huge, I can just sail right through it. I can be through the event horizon, and it's not till I'm, further in that I start getting stretched like crazy.
That's right. If she's lucky, she'll die of old age, but we standing on the outside watching her fall into it will definitely die of old age before we see her cross the event horizon.
The moral of the story is, once you go black hole, you never go back hole.
That's a terrible moral.
Okay, so thank you, Jocelyn, and thank you, Dave. You've pleased me, and your efforts have borne sweet, sweet fruit. I'm sure Kelly will agree.
Woo!
And I'd like to thank my guest, Kelly Weinersmith. Thank you very much for coming on the show and interrupting us when we got carried away.
Thank you for teaching me about black holes.
I hope that you can use this lesson that you've learned in black holes later in life. I'm sure it will come in handy as the days go on.
It will help me understand some of the jokes Zach makes about black holes.
Fantastic. Okay, so you can email the Titanium Physicist podcast at barn@titaniumphysics.com, or you can follow us on Twitter at @titaniumphysics. You can visit our website at www.titaniumphysics.com, or you can look us up on Facebook. If you got a question you'd like my Titanium Physicist to address, email your questions to TIPHYTER, that's TIPHYTER, at titaniumphysics.com. And if you're a physicist and would like to become one of my Titanium Physicists, please email me at physics@titaniumphysics.com. We're always recruiting. The Titanium Physics Podcast is a member of the Brachylope Media, and if you've enjoyed this show, you might enjoy Science Sort of, or the Weekly Weinersmith.
Yes!
So check them out. The intro music is by Ted Leo and the Pharmacists, and the end music is by John Vanderslice. Good day, my friends, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet, jumped through a window out into the hay.